In Chapter 10, we'll be finding the longest shared subsequence, and to do that, we'll go back to k-mers, and we'll talk some more about writing functions, and I'm going to introduce something called a binary search, which is a well-used algorithm that we can use to speed up our code significantly. And so if we go look at the LCSM problem, there's, as always, some nice background that describes what we're trying to do here, and explains that how the substrings can be found, and that, like, for instance here, CG is a common substring of these two sequences, but it's not the longest one. CGTA is the longest one. So we are trying to find the longest one, and in the case where two substrings or more can be found, it doesn't matter which one we return. So we're actually going to use the random module to randomly choose one. So our inputs are going to be 100 length or fewer. They're going to be DNA strings, and they're going to be 100 base pairs or fewer, and of length at 100 DNA strings of at most 1,000 kilobase pair. And they're going to be in FASTA format. So here is the sample here, and AC is one of the common substrings that we have in common here. And so that's what is expected of our program. And so we're going to be talking about how to use k-mers. Again, now we're going to be using them to find shared subsequences. We're going to have lists of lists, and we could just do a couple of for loops to handle that, but there's also something in itertools called chain that will allow us to concatenate a list of lists to make our code a little more streamlined. We are going to introduce a binary search and look at a couple ways to integrate it into our code, and we're going to talk about how to maximize a function. And finally, the min and max functions, we're going to use these, but we're also going to additionally use them with a key argument that is available. So I will explain that to you. So to get started, you should be in the top level here. Make sure that you source the virtual environment in bin activate. I'll do that in, I usually use at least 2 windows to do that. And then I'm going to go into the 10 subdirectory. And with that, I can copy solution 1, it doesn't matter which one, to a program called lcsm.py. I'll overwrite some work I was doing earlier, and we'll see how this is supposed to run by running it with -h. Hopefully at this point, you see it takes a positional argument that's an input FASTA file, and you know exactly how to write that. As far as accepting the arguments and verifying them. And hopefully you also know what we're going to be doing to parse that FASTA file. So let's give it an input. The test that we have here is exactly what we have from the Rosalind page. Those are the 3 sequences that they gave. And then so if I run this LCSM on that input, it finds TA, but if I run it again, it finds CA, and if I run it again, it finds TA, and if I run it again, it finds TA. So it's going to return, and this time it returned AC. So there are actually 3 common tumors in these sequences, and so it doesn't matter which one we return, it's going to pass the test anyway. We can see that if I run make test. We see it is passing all of the tests. You see here, this one's taking a little while. It takes quite a few seconds on my computer. It's a fairly large input, so I'll let that run here, and we'll eventually see that it runs. When I was writing the book, it took somewhere around 40 seconds to run. So that when you start to see that when you give real input to your tests, sometimes it can take a while to pass your test suite, and that can be annoying. And there's also an example where there are no shared substrings. Let's just look at that. Test inputs, it's called none. And so we see this one's composed entirely of G's, A's, C's, and T's, so there is no common substring. So if we run this on that input, then we'll see that there's no common subsequence. The program isn't actually, that's not one of the requirements, I believe, for, it's not something they specifically test, but we should have some good output for our user to let them know when nothing is found. One option would be to simply print nothing, and that could actually be pretty confusing to the user. So I would suggest that we actually write out something like to let them know that it's not found. So to get started, I'm going to run new py. I'm going to, well, let me just copy this real quick. It is going to create a new from scratch version of our program. And I know it's just going to take, I've got all this worked out already, so I'm going to get rid of all of these arguments except for the file.text.io. It is going to be a positional argument, but I'm just going to take this version here. And what I often do is just get rid of the short flag and get rid of that, and now it's just called file. And I believe I have it called something like input, FASTA. It's going to be a file, it's going to be a readable text file. But one thing I want to get rid of default none, because this is a positional argument, and so by default they are required, and so we don't give a default value, don't need that. And so let me double check, yep, that looks good. And finally I want to say I will get rid of these arguments, and I only need to return args.file. Again, it might seem like complete overkill to be using all of this structure, but it's still nice, because if I want to go back and start adding some other parameters to the program, now I have the structure in argparse to be able to easily add those, and I don't have to go retrofit it. So that is how we're going to verify that we have one input file. Let me run with my help. It looks pretty good. Let me run it with some bad input. No, it won't run. Let me run it with the README file. It's going to print that it has the README, because that's all I'm doing right now. And so at this point, we actually can run some tests and see how many we're passing. We know that we're going to pass at least a couple. The program exists, it prints the usage, and it dies on a bad file. So we're already doing pretty good just by having a well-structured program. So let's get into the meat of the program. The first thing is going to be parsing the FASTA file, and the longest common subsequence can be no longer than the shortest sequence that we have. So the first challenge is going to be parsing through the entire file to find the shortest sequence. Now, we have a couple of options. One is to, and we've done things like this before, and so one option is to store everything in memory and then go look at them, and another is to have a running counter to say what's the shortest, and as we encounter each new sequence, we could see, well, is this one shorter than the shortest one I've seen, and therefore update that value. And then when we get to the end, we've only stored one thing, which is the length of the shortest sequence. That is the most efficient way to do this, if that was the only thing that we were trying to do. But we actually are going to need to store all of the sequences in memory, find the shortest one, and then go back through all of them repeatedly to see, well, can we find one that's that long? If not, let's go to the next number and find one that's one shorter, and let's go and see if there's one shorter than that. And so this is going to be a program that's going to require us to put everything in memory, unless you want to get quite clever and find some other ways of caching the data, or if you want to repeatedly read the input file, which could prove to be far slower, but it could also use a lot less memory. So depends on the what you're trying to do and the size of the data set. Really, so often what we need to do is to just write something that works, and as long as it works well enough, then we can suffer through it. If it proves to be unusably slow, then we have to go and find ways of speeding up and using some tricks. I'm going to use the bioseq IO parse to parse through this, so I'm going to need to go up here to the top, and from bio import seq IO, so that now instead of printing the file, I'm going to say for seq in seq IO parse args.file, and I'm going to tell it, I'm going to tell it that the format is FASTA, and I'll print seq. string.seek, because that's what I'm looking for. And with that, let's run our program. Now we will run it on test input 1.fa, and we see we are actually seeing the sequences as they are. We're only seeing the sequences. I'm not printing the IDs, and because I'm printing them, they're just being stringified into the sequence itself. So with that, I'm showing here that if I open a REPL, I can what I get back from seek.io is actually an iterator, and we've seen this before. And so here I'm showing that I can call next on an iterator. I've showed this a couple times, and it will return each one of the records in turn. And I'm just going back over this, we've seen this before, that the seek is actually this sequence object, and that's going to be a problem because I need to stringify it in some instances. Here what I'm showing is a quick way of putting all the sequences into an array. So what I've done here is I've just printed them out, and what I would like to do is put them into some sort of an array. So I'm going to show you a very manual way to do this. First off is just to create a sequences list here, and I'm going to say seeks.append seek, and then I will print the seeks at the end, and we'll look at what we have. And let's just look at that real quick. And what we see here is that we have these sequence objects, which is what I was showing here. This is what the sequence objects looks like. It has some extra data in there like the ID, and if we were parsing a different format, it might have more description or some DBX refs that we could be referring to. But here we really only have just an ID and a sequence line, and I don't care about anything other than just the string version of this. So instead of appending seek.seek, and it might, sometimes I call this rec because it can be confusing. So rec.seek is maybe clearer. But instead I don't want rec.seek, I just want the string version of that. So if I do that and I run this, you'll see the difference is now I just have an array of the three sequences themselves. A shorter way, a single line way that I could write this, and I'll just copy this, seeks is equal to rec string.rec.seek for rec in that. So let me just comment that out. And this is another way of writing the exact same thing. Oh, I need to print it to show you. And you see that I'm able to get the exact same thing, but rather than writing this in 3 lines of code, I've now written it in 1 line of code using a list comprehension. So that's a quick, easy way. I should not say easy. That is a shorter way of getting all the sequences into a list. That is going to be important because I need to find the shortest one. So just a quick aside, we are obviously dealing with a very trivial data set. And even in the largest case, we're only going to have, I think it's 1,000 sequences, and they're going to be only 100 base pair long at most. And so it is very, very common in bioinformatics for sequence files to hold millions of reads. Or they can they could hold only a couple of reads, but those reads could be extremely long. For instance, the human genome, which is 3 gigabytes. So you could exceed the amount of memory on your machine and crash it. I've done this many times. So you may, this solution will work for this input data set. It would probably not scale to a real world data set. And so we would have to come up with more clever ways of doing this, or we would probably need to move to a language where we have finer control over memory usage, such as Rust. And so with that, I would point you back to the GenSeek program that we used before to generate much larger input files to play with, but I'm only going to be focusing on these 2 input files, the second of which actually, even with as small as it is, can still take quite a while to run on my machine. So I show here that another way of expressing this is to write the same idea, the same one-line idea, using a map statement. So you can see all the parts from the list comprehension. So all the parts from the for loop are present in the list comprehension, and then these things just get shuffled around a little bit. The iterator comes at the end, and then in the lambda, I take the record and I stringify the record, and then I map into, so each record from the iterator goes into the lambda, and then I have to coerce that using a list to get all of my items out of the map statement. But if I run that, fh, sorry, I can say args.file, and with that, I get the exact same results. So 3 different ways of writing the same idea. I probably like this one the best. I think it's very Pythonic, and someone other than me would probably not have a problem reading that. Now, to find the lengths of all the sequences, I can use another list comprehension. So let's look at that. I will call this lens, and I will say, let me print that, and then I will print lens. And let's look at what I see there. And now I'm going to clear my screen, and here are my sequences, and here are my lengths of the sequences. So again, I'm relying on a list comprehension. I think that I would definitely not want to write this as a for loop like this. I think this is far simpler, and in fact, I would prefer the very functional way to write this, which would be to say map onto the len function each of the seeks. And the problem, of course, is going to be that that's going to be a map object, so I have to coerce that to a list. So let me comment that out and show you I get the exact same thing, 775. This is just, to me, very clear. If I know that map takes a function, and the function is len, and len takes a string as an object, then each of the strings in seek goes through len and then gives me a list of the lengths. I find that very nice to write. In addition, instead of calling list, I can actually call the functions min or max on these. So given this list, I can find the one that is the minimum length. The minimum number in this list is 5. And so it will return 5, or I could do max as well. And that's going to be important. I'm going to show you some other ways to use min and max in a little bit. So, and I don't actually need all the lengths. I just need to know the shortest one. And so I can call min on that. And I could also call min, I could say shortest on the minimum. Whoops, making all kind of typos. I could also call shortest on that. So let's just look at this. I'll just verify. This is the way I play with code. So 5, that works that way. And I can write it in this functional way also. It also returns 5. So it doesn't matter which one you prefer, but I think this one is quite readable, and it relies on some functional programming techniques. So now I know what my shortest sequence is. Excuse me. So now I want to go back to extracting the k-mers from a sequence, because what I'd like to do is find all the k-mers in each sequence that are of the length of the shortest sequence, and then see if any of those k-mers are shared amongst all of the sequences. And so for that, I'm going to go back to chapter 9. And I can pull in the exact same code that I had before. Now, this is one of the cases where I'm actually going against what I recommend, which is not copying and pasting code, but maybe putting some code into a common module that you would share. Because these programs are living in different directories, it makes it slightly harder to share that. So I'm just going to go ahead and copy and paste the code. And as it is, I went ahead and I put it into the solution. So I'm just going to go grab this real quick from my solution, and it is exactly the same code and test code that we used before, find k-mers, and so I don't really feel like I need to explain any of this, and I have a test for it. I can run PyTest on my LCSM to verify that my function does work. It's not happy because I've imported list, so let me go run this. What I am showing here is that I've made one change to my program and then I've immediately tested it or in some way verified that I haven't broken my code. It's very important that as you make changes that you constantly run your program to make sure that it's still working. So one of the things that we could do is to start with the maximum possible value of k and then count down. And so how do I count down from the shortest? And so I have here, I'm showing in the REPL that if the shortest is equal to 5 and I try to do a range of 5, well, that's going to give me 0 to 5, and if I say list on that, okay, that's 0, 1, 2, 3, 4. Okay, that's not what I want. I want to start at 5 and go down. And so instead of saying 5, I should be saying shortest here because that's the value that we're using. I can't say shortest from 5 to 0 actually because if you'll recall on help not range, it takes 2 or 3 arguments stop. So with one argument it's stop, but with 2 arguments it's start and stop. And if start is greater than stop, then it produces the empty list. So that's not helpful. So what I show here is that there's actually a third argument here that is the step. And so if I give a -1 for the step, then actually it starts to work. So now we are able to count from 5, 4, 3, 2, 1. Another way of doing this would be to reverse a list, reverse a range, give it in the going from 1 up to, and I have to say shortest plus 1 because it will stop at shortest and not include it. So that's another quite much longer way of counting down from a value. So either way that you want, we need to come up with a way of counting down from the shortest. And so here I'm showing in the REPL, I can, from my program, import my find k-mers program. That's really cool. This from pprint, which is a standard module, I'm going to import the prettyprint function. And then I'm going to say for k, and I'm using k intentionally here to help me remember this is a k-mer size. So for k in counting from the shortest down to 0, I want to print what the value of k is, and then I want to pprint this bit of code. Now it's a little condensed, because I don't have seeks. Let's see what I need to do real quick. I can handle this. Tests inputs 1.fa. I can just take this guy and say seeks is equal to that. So let's go back through our for k, print our k, and print our sets. So what is going on here? Well, we know given a sequence like this sequence, I can say find k-mers in the sequence. Let me just hard code the sequence, and I can say what are the 5 mers in that, and it returns this set of 5 mers. And so for the argument 5, it's taking that first sequence that I just showed here, and it's saying find the k-mers on that seek for this value of k. And because the k-mers might be redundant, I'm going to call set on that. We've used set before to create a unique list of values. And so I'm using a list comprehension here to say for each s in seeks, find the k-mers in s for the size k and create a set on those. And so what I end up with is 3 sets representing the 5 mers in each of the 3 sequences. And you see that the last sequence is there's only 1 k-mer because that's the shortest sequence, and that was what's setting our threshold here. That was a sequence that has 5 base pair, and so that's the size of our largest k. And so that is a way of finding all the k-mers in each one of the sequences. You could write more code than this if that seems a little compact for you. I can appreciate that. But I think that's how I'm going to go about finding all of the k-mers in each one of the sequences. And we're building up on some code that we've seen before in the past. And what we're seeing here is that by using this for loop, I'm able to go through 5, 4, 3, 2, 1. And I get all the way down to the single nucleotides. And as you can see here, by using a set, at this place here, I'm just getting back A, C, T, and G. And this last one has no G. So I can see that at the case of the 1-mer, which is at the single base pair, this G is not a shared subsequence because it's missing from this last set. So the question is, how do I programmatically go through this and find the longest shared subsequence? May have given you enough information for you to stop the video and go figure out the rest of this on your own. I definitely recommend that you do try that. Do your best to figure it out on your own. But if you want to stay with me here, I'm going to give you a couple different solutions. So I'm going to show you two variations to solve this. The first version is going to prove to be very, very slow on larger inputs. It's going to be fine for small ones, but we're going to look at some output to show you just how bad it can be. And then in the second version, I'm going to show a binary search that will give us a good place to start looking, a good value for k, and then we're going to see if we can find the maximum value from there. It goes a lot faster, and you are very much encouraged to find something that works even better. So the first thing that we need to do, starting from where we have just finished, is to find the frequency of the k-mers. So then I will be able to say, well, if the frequency of a given k-mer is equal to the number of sequences that I have, then that's a shared subsequence. And as we recall, we only need to find one of them. And it doesn't matter which one, and so I just need to randomly select one and find the longest one. So we've already seen that counter from the first chapter is a great way of counting things. Perhaps my preferred, so much easier than manually writing things. And something I want to show you here is that you can initialize an empty counter without any arguments, and given that, you can call a function called update. So what I have here is I'm putting all of the results of all of this for loop. If I put it into a k-mers, looks like this. What we saw for, and it's set for the shortest value here, so it's going back to 5. If I have this in k-mers and I have counts looks like this right now, I can actually call counts.update using k-mers. Let me see how I did that. Well, let's see. Oh, sorry. So for each group in k-mers, I want to call counts update on that group. Sorry, I can't pass the entire list. So with that, let's look at counts now. And it looks like this. So for each one of the, so now we see here, and let me p-print that actually, might be easier to see. For each one of the k-mers that we have here, we updated with this group, with this set, and then with this set, and then with this set. And when we threw those into the counter, we saw that we got the number of times each k-mer was seen. And you see here that they're all distinct. So we do not have a shared 5-mer. This using this update is a lot faster than having to iterate over each one of the k-mers and then adding them into the counts. So another reason why I like the counter module, the counter function there. So I want to introduce here, rather than having to iterate over each one of those sets, I can actually chain them together by calling from itertools. I can import this function called chain. And so if I chain, if I just show you what that looks like, if I do this and reminding you that this is what k-mers looks like, if I chain them together, then I just get back one long list of all the k-mers. In this case, they won't be duplicated because we know that each one of these is unique. And so now, if I initialize my counts to the result of chaining all the k-mers before, I now no longer have to do the for loop. I don't have to do this code. So this is a compact line of code, but it does several things for me that I don't have to worry about. It's a really quick way of getting the frequency of all the k-mers that are in there. So given those counts, this remember what is the type of counts? Underneath, so it is a collections counter, but underneath it's also a dictionary. So I can call things on it like call dictionary functions like items, and items will return this dict of items. And let me p-print that. Well, actually, it doesn't p-print very well. But what we see here is we get back a list of tuples, which are and if we just look at counts, we see here that the first member of this tuple is the key of this first list, this first entry in the counter, this first key. So that's a key and a value, and then a key, and then those are the keys, and then there's the values. So I can iterate over for key comma value in counts.items, and I can say print key. I'll do an f string here. Key, oh come on, is equal to value. Oops, try that one more time and get the syntax right. And that is one way of iterating over the values. I show that because what I want is to find a value n, which is the number of sequences that I have. N is 3. So when there is a k-mer that has a frequency of 3, then I have a candidate shared subsequence. So I can create this candidates list as to be an empty list, and I can, instead of calling them k and v for key and value, I'm going to give them better names now and say for the k-mer, which is like this 5-mer, for this k-mer and the count, which is the number of times it was found, if the count is the same as n, which is the number of sequences that I have, I'm going to say candidates append my k-mer. And then I can say what does candidates look like? And it's an empty list. So I know that because I've already seen that they are all equal. I mean, they are all equal to 1. That means that they're all unique. So I already know that there are none that will be shared. The answer actually is going to be 2. And so if I change all this, so let's say that I went through all that code and I found that candidates was empty for 5. And then I go to 4. And then I go to 3. I know that the answer is going to be 2. So let me just set k is equal to 2. And we're going to look through this code here. Let's get all the 2-mers for this. What does that look like? These are all the 2-mers that are in our 3 sequences. And I'm going to get the counts of them by calling this code. And now, let's just p-print the counts and verify that it looks like what the book has. Yep, that's what it has. And if we see here, there are 3 that have a count of the number of sequences that we're looking for. There are 3 sequences, and we see that there are 3 tumors that have that frequency. So I need to find those 3. How can I do that? Well, I can initialize my code again here. I go through this bit. If count is equal to k, actually n, sorry, not k, n, then probably better if I just keep copying and pasting. And then if we look at candidates, we see that it finds our 3 candidates. So a very straightforward way of going through each one of the k-mer and counts and finding the ones that have the right frequency. At this point, it doesn't matter which one I choose. I could always just say, you know, if candidates, then, whoops, try that again, print the first one, candidates at 0. And that would be fine. But it would always print the same one, and I find that a little boring. So I think it's important for you to know how to use the random module to just take a random choice from a given set of values. You could find this very useful, especially in writing testing code for your programs, but sometimes you just need to know how to get a random value out of a list. And so that is one way. So with that, I could put all this together into a function that finds the common k-mers in a list. And I defined it, not unsurprisingly, common k-mers. And let's take a look at the list, at the signature for this function. It takes sequences, which should be a list of strings. We have that exactly from our from how we are using the FASTA parser to go through all the records and pull out the sequences. So that's going to be what seeks is. And then we're going to have a value of k, which is going to be starting out at the length of the shortest sequence and going down to 1. And so given those sequences and some value of k, it's going to return a list of all the strings that are common to them. So we're going to put all of these ideas together. And so if I go back into my LCSM, I'm going to actually just jump over to my solution 1. I'm going to find my common k-mers. And I'm going to copy this. And then we'll talk a little bit more about it here. Does not matter the order in which my functions are defined here. So we have this common k-mers. The first thing it's going to do is use this line that we've seen several times. For each seek in sequences, find all the k-mers for a given size that is being passed in as the argument. We're going to chain all those k-mers together. We're going to find a value for n, which is the number of sequences that we've been given. We're going to establish our candidates. We're going to go for each one of the k-mers in the counts. And if it is the frequency of the item, frequency of the k-mer is equal to the number of sequences we have, we're going to append it to our candidates, and that's what we're going to return. And we're never in danger of returning something bad because candidates starts off as being initialized to an empty list. So at the worst, we're going to return an empty list. So how can we integrate this into our program? Well, the first thing that we should also probably do is, let me just check here, we should also write a test for this. And so I have a test for common k-mers, and in addition to testing the code, it also just gives us something to look at. So I'd like to say, okay, given these sequences that we've been looking at, I already know that for a length of 5, there are no common sequences. And so I write that common k-mers for that set of sequences at the length of 5 is equal to the empty list. But I also know that for a length of 2, that the answer is these 3 tumors. Now, I'm returning all of the common k-mers. I could have written this instead to just simply return a single k-mer. I could have, instead of return candidates, I could have said return random choice candidates. And it's totally up to you how you want to write that. If you want to throw the other ones away, that's fine. The testing takes into account all of the possible candidates, and any of the ones that are valid are accepted. So you could always return the same one, and you'll pass the test suite. I'm showing you one way of writing this function would be to return all of them. Maybe under certain circumstances you want to know all of the common k-mers. So given that, I can actually write a main program that is pretty short. So let's go back here and look at what main, how we can clean up main here. I'm going to go ahead and choose commit to one of these. I'll just go ahead and do this functional way here. I'm going to stop printing it. I'm going to make my screen a little wider here. So I'm going to use this list comprehension to get all of the sequences, remembering I need to have them all in memory. I definitely don't like that for finding the shortest, so I'm going to find the shortest one using that little bit of code. And with that, I can write this for loop. So let's just take it one line at a time and think about it. So for a k value, going from the range of the shortest value that I've found down to 0, counting by -1, stepping down, I'm going to say if there are some common k-mers. So I'm going back to using that walrus, the walrus operator. If it's true that common k-mers for this value of k, returns some k-mers, then I want to print one of the random k-mers. Whoops. I just need to indent that. Print a random choice, and then I'm going to call sysexit to exit my program. I don't need to go any further, and the reason I'm going to call sysexit is because I'm going to have this final print statement. So if I were to just simply break out of the loop, then it would print the random choice, and then it would print no common subsequence. So the way I'm writing this is that the only way I get to this line of code is that I've exhausted all values of k and I was not able to find something. I could have set a flag here that said found is equal to false, and then when I found one, I could say found is equal to true. And let me just show you how I could do that. I could say found is equal to false, and then I could say instead found is equal to true, and then I wouldn't have to sysexit. And then I could say if not found, then no common subsequence. That's another way to do this, and that's completely fine, and it's very straightforward. But for this particular program, I can keep it quite short by just exiting the program, and I'm making sure to exit with a value of 0 to indicate that the program exited fine. I want to remind you that if you can call sysexit from anywhere in your program, from some deep inside some call stack, from any function at all, and it will completely stop your program in its tracks right there. That could be a terrible thing. It could be a good thing. Depends on how you use it. I think calling sysexit from main makes a lot of sense. Calling sysexit from some deep other function call, that's a little sus. So with that, I need to make sure I import sys, and I also need to import the random module. With that, I believe I'm going to go ahead and pull up a third terminal so I can leave my window open there. ZSH wants to update, so I go into my work biofx, and then from here I need to make sure I source v&v bin activate, and then cd into my 10 directory, and then from here I can LCSM on test inputs 1. Now let's see, what am I missing? I'm missing counter, so from collections import counter. Make sure I have all of my modules that I need. And from itertools import chain. Let's see, do I have everything now? Okay, it found AC. It found AC, it found CA, it finds CA, it finds TA. What does it pass all of my tests? Now I know this is going to take a little bit of time because that long one is going to take a few seconds. So let's let it run. But it looks pretty good. It passed my short one, so that probably means it's going to pass the long one. So hopefully all of that makes a lot of sense to you now. We've spent some time breaking down each one of these lines of code, so hopefully this bit makes a lot of sense. I can get rid of that line, and that is essentially what I've shown you here. Just a note real quick. If I don't want to use the walrus operator, which looks like this, you see the eyes and the little tusks, it's cute. I could do this on 2 separate lines, assigning common k-mers to something called k-mers, remembering that that's going to return the empty list when there are no common k-mers. And so if I say if k-mers, the empty lists in a Boolean context evaluates to false. So therefore that will be if false, and then it will not print this line. So I now pass my long one, and I also have an additional test for there being no shared sequences, subsequences. So this function, the way that I've written this program does pass all of the tests. And if you're happy with this solution, then I understand, but I would like to show you why it runs so slowly. And so I have this suggestion here that as we go through here, we're going to print k. And I'm going to say, so, right here, print, and I'm going to make it even bigger. I'm going to say k. So I do this a lot in my code so that I can see what's going on. Let's go run our program. So LCSM on tests inputs 1. And we see here it starts at 5, 4, 3, 2, and 2 is when it finds an answer. Cool. Let's see what happens when it runs on 2. Okay, it starts at 1,000 and it's going to run for quite a while because it's not going to find an answer until I believe it's 78. Yes. So we're waiting for this to get all the way down to 78. And as you can see, this is going to take a while. There we go. There's the answer. That's the longest common substring. We don't need to continue looking after 78 because we've already counted down, and so we can stop the program. Very cool. Sure seems like we didn't need to start at 1,000. They were all of the input sequences were 1,000 base pairs long, and it's really, really unlikely that we're going to find something that long. So, maybe we should have started in the middle at 500. The answer, and we could have just said, well, and this gets to like a number guessing game. If we were trying to guess a number between 1 and 1,000 with a friend, we would probably start at 500, and our friend would be able to say, it's too high or too low. And for instance, if they chose 453, their answer would be too high. So if we had started at 500, we could say, do we find something at 500? And we can clearly see here that at 500, we skipped right over it. So we could have said, okay, there's nothing at 500. Let's go down even shorter. Let's go to 250. Which would be half of that, which is exactly how you would ping pong back and forth around the answer here to find the answer of 453. And you know this intuitively that that's a much faster way of finding the answer, and that is a binary search. It is an age-old algorithm that has been used for such a long time. And so I'm going to show you how to write a binary search. So for that, I've included a program called bin search, and if we look at how this runs, it takes some number that we're trying to guess. So we're going to establish this right off. Let's say bin search. Let's run it with -h. So if I run it with -n, like let's say I'm looking for the number of 453, and there's going to be out of a maximum range of 1,000, then we see how long it takes to find 453. So it takes what it's going to be printing here. Let's just look here. It's going to, print the low and the high range that it's looking at every time it goes through the binary search function. So it's going to start at 0 and 1,000. And it looks at the middle number. So it's going to look at 500. And it sees that 500 is higher than the number it was given. It doesn't know what the number is in here. Well, I guess it does. But it sees that it's too high. Obviously, it could just print the number. But we're trying to show what a binary search looks like. So it then cuts this in half and says, okay, I looked at 500 and that wasn't that value was too high. So I need to look at all the numbers less than that. So it goes from 0 to 499. The number 453 is in the middle of that. So when it looks at 250 and it says 250 is too low. So then it says it sets 250 as the bottom and 499 stays as the top. And you see it keeps moving the window smaller and smaller until it converges to 453, and that is the number. And so how does it do that? We create all the numbers 0 to 1,000 by doing a range going up to the maximum +1. Remembering that normally range would not include the last number, so I have to add 1. So those are all the numbers that I'm looking at. and I'm going to try to get the position. And when it's not found, like for instance, if I said I'm looking for 453, but the maximum is 100, then it would see that in the numbers 1 to 100, 453 is not present. And so in the end, if it gets through all of this code and can't find it, it's going to return -1. So what it's going to print is it found the number if the position returned from binary search is greater than 0. Otherwise, it's going to print that the number was not present. And you see here that this is one function call. It's not this big list here. It's a call to my binary search function. And what's interesting is that the binary search function itself calls the binary search function. It is a recursive function. And this gets into some real computer science stuff that could be extremely helpful to you as you're trying to write really interesting and more advanced code. You really need to know how to write a recursive function, and binary search is a classic example of a recursive function. So inside of this, let's talk for a second about the way I called the arguments to this. Given an x, which is an int, in this case it's an int, but I want to stress that it could just be anything that is comparable. So it could also be a string. Strings can also be compared as greater or less than. For instance, if I say, a is less than z, that's actually valid because underneath there is an ordinal value for a, and it is 65, and there's an ordinal value for z, and so it is true that a is less than z. So these don't actually have to be ints. They could just be as long as the list is homogeneous and all the things in that list can be compared as greater or less than, then binary search will work on that data type. So even though I'm restricting it to int here, it doesn't need to be an int. So I'm calling this x to say it's something. It's some unknown value. And the list of values that I'm looking in is called x's. That's the way I pronounce this. And that's a very functional programming way of talking about this. So given some value and values, I want to restrict it between the lowest value that's in this list and the highest value that's in this list. Again, it's stressing that all the ints in this line could be replaced with just some other data type that can be compared. So it's actually a very generic function. So looking for this x in this x's in the range of low to high. So what happens is if the high is greater than the low, then we can go through this list. If it turns out that we've converged, like when we were looking for 453 inside of 0, inside of 100, at one point we finally get to the place where the low value is actually greater than the high value. So that's an indication that we've exhausted all the values, and so we've not been able to find it. So that is our base case. That is how we know when we need to leave our recursive function. Without the base case, this would recurse indefinitely, so we don't want that. So if this condition is met, then we're going to go through this. Otherwise, we're going to return -1. So the first thing I do is I say, what is the midpoint between this? So this is actually the value that's in the middle, and the position in the list of x's, the position that's in the middle. And I say, if the thing that is in our x's at the position in the middle is equal to the thing that we're looking for, then we return the middle, the index where the value can be found. If the thing that's in the middle is greater than the thing that we have, we're going to run binary search on going from the low up to the middle. So we're going to look at the left half of the list. We're going to search the low values. If this is not the case, then we want to look at the high value, so starting at the midpoint and going up to the high. And that is how we continually divide our list in half. And so this turns out to be far more performant than the linear search. So the linear search grows by the number of elements in our list. So when it was 1,000, The worst case runtime would be that we have to look at 1,000 sequences to determine that there is no shared subsequence. This turns out to be log of n, so we have to do it's always a fixed maximum number of searches that we have to do, as long as that list is sorted. That's a crucial part of this. So to add this into my program, I'm going to take a version of this. So let's go into our LCSM, and I'm actually just here. I'm going to copy solution to binary search to LCSM, so I'm not spending too much time getting my code copied over. So let's talk about how I would incorporate this into my program. So given, and it might be easier to read here on this. So let's go down here. So this is what our main can look like now. I'm going to use still the same list comprehension to get all my sequences into a list. I'm still going to call this shortest line to find the shortest one. But now I'm going to do a partial function application, which we've talked about before. And I'm going to say, because common k-mers, if you recall, let's look at common k-mers real quick. Common k-mers takes as its first argument the sequences. So the sequences are always going to be the same. It's always going to be the sequences that we're looking at. So I can partially bind common k-mers to that value. And now I only have to, in order to call that function, I just have to pass a value of k. So I'm going to create this common. I'm just going to call it common now. I can't call it common k-mers because then I would be overriding the common k-mers function. So I'm going to call this common, and I'm going to get a start position by calling binary search using that function, and I'm going to go and I'm going to say that the lowest value it could be is 1, and the highest value it could be is shortest. So this looks exactly like, if we look at, real quick, the bin search. What we looked here is we're calling this binary search for this number that we're looking at we're searching in these numbers, and this is the low and the high, right? The low and the high. And that's what I'm passing here, the low and the high. And from this low to this high, I want to take each of these values and run common. Common is a partial application of common k-mers with sequence. So it looks like this. If I find a place in here to start, then I have this other code that I have from before. Now I have greatly reduced the range where I need to look to do a linear search. I'm not using binary search here to find the exact answer. I'm using it to find a very high starting point and then seeing if I can maximize it from there. So if it's true that start is greater than or equal to 0, because remember I've written my binary search to return, let's go back to this version, it's going to return -1 if the value can't be found. All of this code is just a modification of the bin search that I used here. And instead of looking at the values in high and low, I'm calling f. So I'm actually, instead of this f here is a function, which is something that is callable. So I can say, call the function on the high value and call the function on the low value and assign those to the values high and low. And then I can look at, I can try to find a midpoint between those two. So, if the low is 1 and the high is the shortest sequence I found, I can say, what's the value that's in the middle? And then I go through all the same kind of stuff here that I've done before with the binary search that I explained. If high and low, if I've got a value for both of those, I'm just going to return the high value. If I get a high value and I do not get if I get a low value but I do not get a high value, I'm going to recursively call binary search on using that same f, but I'm going to go from the low value to the midpoint. And if I got a high value but not a low value, I'm going to search the other half of the list. I'm going to call binary search starting from the midpoint and going to the high value. So that is how I've turned that binary search into something that instead of looking at a specific value in a list, I'm calling the function with those values and trying to find a value. So this will give me just a starting point for where I can look. And if that's greater than or equal to 0, then I'm going to go from k, starting at that place, going up to the shortest value plus 1. I should never ever have to go very, very high. This will get me in the range very quickly. And to show how this works, let's print k now. I'm going to print that same f string with k here. Whoops. I mean to put it here because I don't have a k there. And let's go through this. So now our LCSM, we're going to take this on tests inputs 1. If we run this, we see it goes to 2 and then 3 and finds it's going to be 2. So let's run it on our bigger data set, and we see here it starts at 63. So our binary search cut out a huge amount of search space, and it said 63 seems to be a place where we could start. And there definitely is a common k-mer at 63. If there's one at 78, then we know that there's one at 63. So it goes and goes and goes, and it keeps track of all of this, and it does 78, and when it gets to 79, it sees that it can't find one, and so it prints the longest one at 78. And so how does this work? If the binary search found something, then we have these candidates. And now you'll see here that instead of candidates appending all of the candidates, it's just appending one random choice of the k-mers that were found. So if it's true that common for this size k returns some k-mers, then just take one of them randomly. And again, I could have written common to only return 1, and then I would have just moved the random choice into that function. Totally fine that way too. And so now I have all of these candidates. If I get to the place, like here at 79, where I do not find any common k-mers, then I break out of my list. And now I have this list of candidates that are all different sizes. So there's going to be one candidate that's 63, another one that's 64, all the way up to 78. And what I want is the candidate that is the longest. And so there's a quick way to find that. If we know here that the max function, given this list of 4, 2, 8, and 1, will return 8. But given this list of sequences, what I want is the longest sequence. I can't call, let's just look at this real quick. Let me go back into my REPL here, and let's just say seeks is equal to this. If I say, what is the max of seeks? It's going to say TTT because it's comparing them to each other. So is it true that GGG is less than TTT? That's true. Is it, maybe it's easier to write it the other way. Is it true that TTT is greater than GGG? That is true. So when we call max on this, and this is what I was talking about earlier, strings are comparable to each other as greater than or less than. So if I call max on that, it's going to find me the one that is greatest according to the way that strings are sorted. That's not what I want. I want it to find me the one that's the longest. And so I'm showing here in the book that instead I could do this list onto the length. We've seen this before. I was using it earlier. So they are lengths 1, 2, 4, and 3. And so what I want is to use those values to return the thing at this position because that's the one that's the greatest. And so to do that, I can say, tell me what the max is of sequences. But the key is that I want you to run the function len on the values before you find them. And now it finds that the longest string is GGGG. And that is exactly what's going on in my code, is that I want the candidate that is the longest. I want to maximize for the length of the candidates. And that's how I print the longest one. And for each value of k, I'm only saving one random k-mer from that. It doesn't matter which one. So, and here I dig a little deeper into how I modified the binary search from the bin search program. So that now it's, instead of looking at a specific value in this list, it's calling a function using the low and the high values. which is a pretty interesting way. This is what makes this a higher order function on a couple of levels. One is that the function itself takes another function as an argument, and then it can actually, well, that's what makes it a higher order function. What makes it recursive is that it calls itself. That's what the next thing I was going to say. So, but the recursion also passes in f, and I'm using f. Arguably not a great variable name because it's a single letter, but it's one of those very special letters where from mathematics, we say f of x all the time. We know that f means function. So this is some sort of a function. Perhaps I should have called it fn. Maybe it would have been a little nicer name. So for some function that returns some value that I can have for high and low, and I'm having to call these hi and lo to distinguish them from the high and low values that are being passed in. So that's a little confusing. It took me a little while to write this, obviously, but once I really pretty much had to write the bin search program to prove to myself that I understood how a binary search worked, and then I modified it into this to use my function of common k-mers to help me find the answer. So it's a rather involved solution that uses a lot of advanced programming techniques that I've talked about up to this point, but hopefully it makes sense to you now. And hopefully one of the things that will help to make sense of it is that there is a test in it. So given these sequences, the first three sequences that we've been playing with all along, I create this F1. It's a partial application of common k-mers, which is another function in this scope, and I'm binding seeks1, and I'm binding this into a function called F1, and that is a partial function application, and I'm calling my binary search function using F1 from the values 1 up to 5. And I know that the answer is 2, that it should find that the place where binary search converges and it finds an answer is 2. And when I do this for these sequences here, I'm binding a second function onto those sequences, and I'm looking for between 1 and 6, and I find the answer is 3. And I arrived at that by running them and finding the answer, but writing out the test helped me to understand my functions even better. So and I have here, unlike the previous binary search, this won't necessarily return the exact answer, just a starting point. But if there are no shared subsequences for any size k, then it will help me find that. So this is how I go about testing these functions. I do have access to, this one suffers again from the same problem with running on a Mac, so I can't run this on my laptop. I could jump over to a Linux machine and run the benchmarking, but this shows you how I'm using hyperfine here to determine which one is faster. And you see here there's a huge difference. The binary search is somewhere around 28, 29 times faster than the functional search. So I would definitely go with binary search, even though it's a rather complicated program. It goes from a linear search down to a log-n search, and we have a little discussion here about big O notation, how we would write that. The first one is ON, which is a completely linear search, whereas the binary search is log of n, so incredibly much slower, and always a defined maximum number given any size n, that you will never go beyond log of n comparisons. So very much worth learning how to write a binary search. As with Chapter 9, I suggest that to go further with this program, you might include a Hamming distance that will allow for how many differences on shared k-mers. So like k-mers that are close enough, right? And maybe you would like to come up with a solution to this program that doesn't use k-mers, that somehow uses, well, you're still going to essentially be talking about k-mers, but without necessarily pulling out all the k-mers. Maybe you're going to look at starting positions and scanning over the length of the strings for different substrings, I definitely recommend you come up with as many different kinds of solutions as you can. And most importantly, learn how to benchmark them against each other. Figure out how to determine what is the worst case runtime scenario can be. So to review what we talked about, we again relied on k-mers. And we were finding conserved regions of sequences. And so, there, from a biological standpoint, some conserved sequence shared across a bunch of other sequences that could indicate some sort of commonality between the sequences, maybe some sort of a coding region or some sort of a reason that evolution has decided to keep these regions, but they are not always exactly conserved. This is where we get into sequence alignment and finding sequences that are close enough to each other, which is one way we could look as Hamming distance, but again, that doesn't take into account insertions and deletions, so it's not an extremely great way of finding matches, but it's something that's not an exact match, and it's very rare that we find exact matches in biology, especially because of just errors in sequencing. So this gets you at the problems that we deal with in finding conservation in sequences. I talked about that lists of lists can be combined into a single list using itertools.chain. We talked about how binary search can be used. Very crucially, it has to be reused on sorted values, but it is much faster than doing a linear search, starting from one end of the list and going to the other. I talked about a hill climbing way of maximizing this function, that I use my binary search really just to find a starting place. And finally, I talked about that there is a key option for both min and max. That is a function that is applied to the values before comparing them. And we keep seeing these ideas of functional programming coming up, even in the built-in functions inside Python, that they themselves are higher order functions. So key takes a function. And that's a lot of what we're doing here in the way that we wrote this program, is that we're relying on passing around functions. For instance, here I'm passing this function len to map, but then I'm also passing len as the key to max. And so we see this, and so therefore that's why I do things like this partial function application, so that I can then pass that partially applied function to my binary search. You may or may not like my style of functional programming, and again, I stay as far away as possible from object-oriented programming. I'm sure that you could come up with an OOP solution to this that would look incredibly differently, but I find that I find the code that I end up writing to be more readable and shorter than comparable OO solutions that I have seen.